Okay, in this video we're going to talk about UV Vis spectroscopy. This is something that you might use both in chemistry and biology quite a bit. You're simply looking at the absorption of light in the ultraviolet and the visible range. So we'll talk a little bit about what that spectrum looks like, how we should think about absorption versus color. And then we'll kind of get into the chemistry part of it. So how can we understand how molecular structure affects the UV vis absorption of a compound, and particularly how conjugation of pi bonds is really, really important here. From there, we'll try to get a molecular orbital picture of what's going on. For the most part, we are going to focus on what's called a pi to pi star transition. So how are the pi orbitals interacting to give us these different absorption frequencies? We'll focus on something called the chromophore. So the chromophore is just the part of the molecule that gives it its color. And then we'll draw a connection between conjugation and compounds that have antioxidant properties, so like blueberries, tomatoes, etc. Okay, so first, here's the electromagnetic spectrum. You've probably seen this before. We've got this broad UV range. That 254 nanometer peak is usually the light that we use for TLCs, for instance. There's also a long-range UV light that we use sometimes. That's around 350. The visible range is about 400 to 780 nanometers. And then it goes into the infrared. Infrared spectroscopy is kind of a whole different thing that we'll talk about, I think, in the next video. On the right, you see what's called a color wheel. So remember that when we see color, what we're seeing is the light that is not absorbed by the compound. So if I shine, for instance, a white light on something and it looks green, that's because it's absorbing red light. So if we look across the color wheel, that kind of shows us the correlation between the color absorbed and the color seen. All right, so compounds, most organic compounds are white, right? Because they absorb either in the X-ray region or in the UV region. But as we start to absorb violet light on the very, very left side of the spectrum, if we absorb violet light, our compound starts to look a little bit yellow. And as we absorb, as our absorption keeps going to the right, now we're absorbing a little bit in the blue, maybe the blue-green. Now we're starting to see it shift from yellow to orange to red. So that's kind of how it goes. Again, that's why most organic compounds are kind of in that white to yellow to orange range, is because they're absorbing either in the UV or just a little bit in the visible range. So here is the big idea in this video. So we looked at molecular orbitals quite a few weeks ago. So on the left you see ethylene. It's got a pi and a pi star orbital. Again, these are all p orbitals. So the pi orbital has two p orbitals in phase. The pi star has those p orbitals out of phase, not mixing. When we add two pi orbitals next to each other in butadiene, the picture looks a little bit different, right? So now we've got, our two filled orbitals and our two antibonding orbitals. But notice that the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital is shrinking, right? So if you go by the numbers on the bottom, it says 185 nanometers to 215 nanometers. What does that mean? So essentially, these compounds can absorb a photon with an energy that matches that HOMO-LUMO gap. Okay, so, and the bigger the gap, the higher energy photon it absorbs. So ethylene has a very high gap, and so it's going to absorb way, way to the left of the UV. Butadiene has a much smaller gap, and so it's going to absorb a lower energy, higher wavelength frequency photon. Okay, again, higher wavelength is lower energy. If we keep stacking pi orbitals next to each other, we get to octatetraene, right? So here, now our HOMO-LUMO gap, as we call it, is quite a bit shorter. And so it takes a lot less energy for me to bump an electron from this level up to this level. Okay? That's why octatetraene is colored. So it absorbs at the 400 nanometer range. Again, a lower energy photon is required to bump a pi electron into a pi star orbital. That is called a pi to pi star transition. And that's primarily what we're talking about when we talk about UV Vis spectroscopy. It's that pi to pi star transition we can focus on. Okay. Now, the longer we go, the shorter that HOMO-LUMO area gets, right? So polyacetylene is basically, just picture a really, really long chain of like 100 of these things all together. Now that HOMO-LUMO gap is shrinking and shrinking, and now it's definitely visible. Maybe it's even in the infrared. So polyacetylene is very highly colored. It's actually a conducting polymer. This HOMO-LUMO gap is really important to semiconductor design, and so these compounds not only absorb light, but they might serve as useful semiconductors. What do these spectra look like? So here's a very simple molecule, 2-propanal, common name acrolein. So we usually think about the Beer-Lambert equation. Again, if you've taken analytical chemistry, you are well familiar with this. A, absorption, B is epsilon is the molar absorptivity, C is the concentration of the compound, L is the path length. So I show you this spectrum on the y-axis. We've actually got molar absorptivity, and we can see the peak here at 202 nanometers. That's our strong pi to pi star absorption, because we've got some conjugation in this system, right? It's similar to the butadiene that we saw on this slide. But we also see a smaller peak at 340 with a lower molar absorptivity. So that is called an N to pi star absorption. That's a lone pair on oxygen going up to pi star. So if you think about the lone pairs are going to be in the middle here, and it's easier for us to take an electron to go the shorter range there. But because of various reasons, that is less likely to occur, and so we see kind of a smaller peak there. So again, we're going to mostly focus on these big peaks that are pi to pi star interactions. Okay, so here is a TLC. You might recognize it from your homework set, but this is spinach extract. So you can see lots of different spots on this TLC plate. A lot of times we would do this in person if we could. So I just want to point out a couple of the spots here. So one thing is we can see two orange spots. One orange spot at the very top of the plate and one orange spot near the bottom. The orange spot near the top is beta-carotene, which is shown at the bottom where R equals H. But if that R is an OH, if it's a hydroxyl group, then we have xanthophyll. And xanthophyll is quite a bit more polar because it has that OH. But what I want to point out here is that both spots are orange, and they are the same shade of orange. That's not surprising because they are orange because of all those pi bonds that are conjugated to each other. So we would say that beta-carotene and cryptoxanthin have different polarities due to that hydroxyl group, but they have the same chromophore. They have the same array of pi bonds whose molecular orbital kind of interactions give it that same pi to pi star distance, and so the same color. So the chromophore gives it its color. Notice that the OH in chromoxanthin is not conjugated to that chain, and so it really shouldn't affect the color at all, and it doesn't. Okay, now we can also briefly compare two chlorophyll dots. So you can see chlorophyll A and chlorophyll B in the middle of the plate. You can see they're both green, but they're just a little bit different shade of green, and they're a little bit different polarities. The difference between chlorophyll A and chlorophyll B is that formyl group, that aldehyde on the top. That carbonyl is conjugated to that conjugated ring in chlorophyll B. Right? So this pi bond is conjugated to that pi bond. So that's going to make it not only more polar, and so we can see that in the TLC plate, but because it's conjugated to the chromophore, it's actually going to change the color a little bit. So if I've got functional groups either dumping electrons into the conjugated system or taking electrons out of the conjugated system, I'm going to see a change in color. So you can see these pigments look pretty dissimilar, right? Chlorophyll is a big ring of delocalized electrons. Beta-carotene is more linear. We can see lots of different ways to have colored compounds. When we talk about especially natural dyes, when we are trying to get more safe coloring compounds for foods and processed foods, for instance, we're reaching to stuff like crostin from saffron or alizarin or beta-carotene like we saw earlier. On the right, you can see indigo, which was really important in early textile manufacturing, and Tyrian purple, which was even kind of more rare and valuable. But that's a great example of what we were just talking about. The Z would be a bromine or a hydrogen, and if you add a bromine to that conjugated system, it's going to change the absorption frequency just a little bit, and so it's going to change your color absorption from indigo to that more reddish purple. Sometimes it's called an oxychrome, but you don't need to memorize that word. Here's beta-carotene and lycopene. Beta-carotene is orange from spinach, orange from carrots. Lycopene is red from tomatoes and just about every other red thing in nature. You can see the UV Vis spectrum below, pretty similar but a little bit off-shifted. So the main point I want to talk about is the connection between what we've been talking about in terms of HOMO-LUMO gaps and color and antioxidant properties. Okay, so lycopene is well known as a good antioxidant. People talk about the Mediterranean diet and the sort of health aspects that brings. And so what do we mean when we say antioxidants? When we say antioxidant, what we say is that it is reacting with a radical species in the body. So there are lots of radical species. There's reactive oxygen species. There's sort of carbon radicals. A radical is an odd electron source, so it's only got sort of one electron, not a lone pair, or something like that. And these radicals can often act in a catalytic way to cause damage in the body. So compounds like this, compounds like lycopene, have a relatively high energy HOMO, high energy, highest occupied molecular orbital, and a low energy LUMO. And so it can react with radicals depending on whether the radical is electron poor or electron rich. So lycopene can give up an electron to an electron poor radical, or it can take an electron from an electron rich radical. Either way, lycopene is pretty happy to carry that odd electron because it's so conjugated it can just kind of push the odd electron up and down the chain. And so that lycopene radical being stabilized isn't going to cause further damage, isn't going to catalyze like cell membrane breakdown or anything like that. So this is the kind of amazing thing. When you hear that your diet should include like colored fruits and vegetables for their antioxidant properties, you can actually connect the antioxidant properties with the color. They are antioxidants for the same reason that they are colored. It's because they have that small HOMO-LUMO gap, right? In color terms, it means I can promote an electron up from the HOMO to the LUMO pretty easily. And from an antioxidant property, it means that it can both take and receive an odd electron pretty easily. So, eat your fruits and vegetables.